evening, everyone, and welcome to tonight's Evnin Public Lecture, presented by Princeton University's Council on Science and Technology and co-sponsored by the Department of Physics. So we want to acknowledge all our sponsors. The support for the Council's annual public lecture comes from the generous donation of Tony B. Evnin, who was a Princeton class of 1962, and he's the director of the biotech company Venrock Associates. I'm Naomi Eric Leonard. I am professor in mechanical and aerospace engineering and also director of the Council on Science and Technology. Our council fosters university-wide engagement in science and engineering, exploring the societal impact of science, technology, engineering, and mathematics, often known as STEM, promoting innovative teaching and research, and new ways to live at the intersections of STEM with the arts, humanities, and social sciences. We seek to ensure that all students graduating from Princeton can be exemplary citizens, voters, and leaders with the ability to assess and appreciate the science and engineering issues of the day. So tonight we have a wonderful guest and lecture in store, and I'm really delighted to see so many of you here. It looks like we have a packed room. But to introduce our speaker, I'm going to turn it over to Professor Dan Marlowe from the Department of Physics.
Thank you, Naomi. So it's really a pleasure and an honor to introduce our speaker, Nergis Mavalvala from MIT. Obviously, she works in the LIGO collaboration as the linchpin of the LIGO collaboration. A little bit about Nergis. She was an undergraduate at Wellesley, went and did her graduate work at MIT, where her thesis was already working on LIGO, and she's won many awards. I have to consult the list on this. Actually, before I get to that, just let me mention more about her career. After MIT, she went out to Caltech for a while, then back to MIT, where she rose through the faculty ranks, is now associate chair of the department. My condolences.
Thank you.
But obviously, or associate head, I guess, at MIT. Obviously, she's well thought of by her colleagues. And many prizes. The list is too long. I don't want to cut into the time for her talk, so I won't read the whole list, but some of the highlights. She shared the Breakthrough Prize with her colleagues from LIGO. She's a fellow of the American Physical Society, won the Keithley Prize, which is another APS prize, and last, certainly not least, is the MacArthur Prize, or MacArthur Award, which is also called the Genius Award. And I think that's a fitting, well, it offers me a segue. So the aphorism is genius is 91% inspiration, 99% perspiration. And I think that's really true of LIGO. The idea to look for gravity waves is obviously inspirational, but it's easy enough to say, let's look for gravity waves. The hard part, which I trust we'll hear about, is how do you actually do that? And this is just an incredible technological, scientific accomplishment. And there's all kinds of science that goes into just making the instrument. And this is where Nergis has really played a leading role in working out all this stuff, starting with her thesis, and I assume lots of hard work between then and now. So without further ado, let me introduce Nergis.
Good. Can everyone hear me? Great. Good. So thank you very much, Dan, and thank you all for being here. I actually have to say I love coming to Princeton because I have so many colleagues and former students and students who I hope will be my future students. So it's wonderful to be here. And so what I want to talk about today is this. Oh, I want to get the lighting right before I do that. I don't do this to put you all to sleep. I do this because the graphics will show up better. So I'm going to talk to you about the discovery of gravitational waves that sort of made the news headlines a little over 2 years ago in February 2016. And what I want to tell you is that this is a completely new way of looking at the universe. Everything I'm going to talk about today is really the work of over 1,000 scientists who collectively belong to the LIGO and Virgo collaborations. And so even though I'm speaking to you today, really this is the work of many, many more people than just myself. So my story will begin with the announcement for the 2017 Nobel Prize in Physics, which the Nobel Committee said was awarded for a discovery that shook the world. And I really like this way of phrasing it because it was both literally and figuratively true. And so let me sort of unpack what that is. So the Nobel Prize went to these three gentlemen here, and it was for decisive contributions to the LIGO detector and the observation of gravitational waves. And so what I would like to do is I'm going to go through, in my talk today, tell you a little bit about what gravitational waves are, why it was so important to observe them, and how it was done. Okay, so on the left here is Ray Weiss, who spent his academic career at MIT. He was my PhD advisor. And then from Caltech, on the right here, Barry Barish and Kip Thorne, who I've also worked with. And I just wanted to sort of make a clarification to something that Dan said. This discovery was 200% inspiration and 200% perspiration. And so now you can also see that I'm not really a genius because I can't even do math. But it was really, you needed both in tremendous measure, and these were the founding fathers who provided those things for us. So the claim I made in my title was that this is a new window into the universe. But to really, if you want to sort of talk about a new window into the universe, first we must know what the old window into the universe was. And that, for millennia, as long as humans have recorded our thoughts about this, has been light. And so here is an example of an object that we might see in the sky. This is a supernova remnant. What happened to this object? This was actually a star not dissimilar. This is Cassiopeia A. And it was a star pretty similar to our own sun. And then about 300 years ago, it ran out of the nuclear fuel that makes stars burn. And when stars run out of nuclear fuel, they stop shining. And when they stop shining, the pressure of the light that holds them up against their own gravity turns off, and the star collapses. And in the core of the star collapses, the outer layers are shed, and this is the picture we're seeing. And all these three different colors that you see are actually it's a composite picture taken by the three great observatories of NASA. So the reddish colors are infrared light, which our eyes can't see, but of course snakes could see. And it's the lowest energy emission of photons. The yellows and greens are optical light taken by the Hubble Space Telescope for that part of the image. And then finally, the blues and purples are the most energetic photons, or X-rays. Now, if you could draw your attention to the very center of this image, you'll see a small little blue dot right here. And this is only visible with X-ray emission. And this little blue dot is an object called a neutron star. And it is, in fact, a very peculiar object. It has the mass roughly of our own sun, but its radius is 10 kilometers. So it's the size of a small town, but the mass of our sun. Now, compare it to our sun has a radius of 700,000 kilometers. So this is an extremely dense, compact object. And this object is formed in the process of the death of stars that are about the mass of our sun. Now, if this parent star had been a little bit heavier, if it had been 3 times the mass of our sun, or a little bit more than that, the gravity of all that mass would have caused this neutron star to continue to collapse until it would have turned into a black hole. So lesson number one, neutron stars and black holes are cousins in that they're born of similar processes in the deaths of ordinary stars. Now, if it were a black hole, how might we see it? Black holes get their name, actually coined here on this campus, for a good reason. They're mostly black. And the reason for that is that they have so much gravity that even light can't escape they have so much mass in such a compact volume that even light can't escape their gravitational pull. But even so, people have seen black holes by inference. So here is an artist's rendition of an object that's believed to be a black hole, in this particular case, J1655-40. And what's shown here in this artist's picture is a black hole that's accreting matter from a companion. So all this material, gas and dust, is falling onto the black hole due to its gravity in this sort of swirling whirlpool. And the inference is made by looking at the light that's emitted. So this is an observation with the Chandra X-ray Observatory. And this object glows in X-rays because of all this material being heated up and emitting light. Now, most black holes, we don't expect to be sitting in a region of space where there's a companion for them to accrete material. If there was no companion from which this black hole could accrete material, it would be truly black. There would be nothing to make it glow. And that then brings me to the question of how might we then observe those black holes where we don't have any material, any matter accreting, so that we can observe them. And that brings me to our new window, our new messenger, and that would be the one property of black holes that we do know about is gravity. So to really work with that, we need to understand how gravity works. And so we start in the 17th century with our first hero of gravity. And our first hero of gravity was Sir Isaac Newton. And Newton had this very successful universal law of gravitation. And it was actually he had a mathematical formulation for it, where we basically could say, well, if I have two objects of mass m1 and m2, and they're separated by some distance r, I can write down quantitatively that they will experience a mutual force that's proportional to their masses and inversely proportional to the square of their separation. Now, Newton actually worried about something that never got solved in his lifetime. Newton worried about this question of action at a distance. And what that means is Newton asked this question, how does this mass 1 know about mass 2? How do they influence each other? In modern parlance, we would say, what mediates that interaction? How do they exchange information? And therefore know that they should be attracted to one another. And that conundrum, and this is something that even Aristotle, a millennium earlier, had worried about, how objects influence each other without touching. And this conundrum of Newton's didn't get solved until our next hero of gravity came by, and that was Albert Einstein. And in the early 20th century, Einstein gave us a new theory of gravity. It's called the general theory of relativity. And Newton told us something quite remarkable. Einstein told us something quite remarkable. Einstein said this idea that gravity is a force is a construct. Really, gravity is geometry. And the way that Einstein then thought about it is that all of space-time is a medium that can be warped by the presence of massive objects. So the simple-minded way, and not fully correct, but certainly good enough for the way we'd like to think about it today, is to think about space-time as a rubber sheet, or a cushion, if you like. And if you place a bowling ball in the center, the surface of the cushion will curve inwards. And then if you put a small playing marble at the edge, the playing marble will fall towards the bowling ball because it must follow the curvature of the cushion. And if you take that analogy to the geometry that Einstein described, then you would know that gravity is attractive because the massive object curves the space-time, and then a test particle must follow that curvature and fall towards the massive object. Now, like Newton, Einstein also wrote an equation. And Einstein's equation looks almost as benign as Newton's equations. Einstein's equation connected the energy associated with these gravitational objects to the geometry of spacetime. And it looks just as benign, but it's actually in reality a set of many equations and very, very beastly. So, and that has been one of, Einstein wrote this down in the period between 1915 and 1918, and it has taken the better part of a century to come up with exact generalized solutions for these equations. And in fact, some of that groundbreaking work on exact generalized solutions was also done by a Princeton colleague here, Franz Pretorius. Okay, now Einstein then went on to ask the next question, which was, what if this object, say our bowling ball, our hypothetical bowling ball, wasn't just sitting on the cushion? What if it was actually bouncing up and down? Then what happens to the space-time or our hypothetical cushion? And what he found out of his equations was that the surface of the cushion would ripple. And very much like if you dropped a rock on the surface of a still pond, that ripples would spread out from where the rock was dropped. And that was then the picture of what would happen if this massive object was accelerating, if it was in motion. And then the picture that can derive from that is if you had two objects, in this case maybe two neutron stars, if they were orbiting each other, the space-time around them would be distorted in the form of this wave, and this wave would travel outwards at the speed of light. Now, Einstein was very ambivalent about these ideas. He gave us this very, he formulated the theory of general relativity between 1915 and 1918. In 1918, a physicist by the name of Schwarzschild actually took Einstein's equations and understood that they contained in them are stars that have so much mass that the light cannot escape their gravitational pull. At the time, these were called dark stars, and there's correspondence that shows Einstein did not think nature could make such things, these dark stars. Einstein vacillated even on the existence of gravitational waves. In his 1916 paper, he dismissed them as having no practical purpose. And then in 1936, he actually wrote a paper retracting their very existence. And then in the same year, he retracted the retraction. And so you can see that he was really unsure about whether these exist. Now, I'm an experimentalist. I build experiments, and so I take great pleasure in saying that ultimately observation and experiment have the final say. We have to ask, does nature behave this way? And this was a theory until then, right? So there was a lot of work and doubts and controversy that finally subsided in the 1950s, but experiment and observation will have the final say. So let's see what they said. So the evidence mounts. In 1934, two physicists, Body and Zwicky, proposed that there could be these objects called neutron stars, which I've already introduced to you, stars with the mass of our sun, but a radius of a few kilometers. In 1967, Ficini and Gold proposed that these neutron stars could be rapidly rotating, and that rapid rotation could give rise to very strong magnetic fields, and what that would do is that would make the starlight be beamed like a lighthouse. So instead of like our sun that radiates in all directions, these stars would have lighthouse beams that could cross our line of sight as they rotate. Now, those are called pulsars, by the way, that version of a neutron star. That same year, the first pulsar was observed by Bell and Hewish. And then in 1969, this man, Joe Weber, announces that he has detected gravitational waves using a device that looks like this. This is actually a big piece of metal, about a ton of metal, in this case, an aluminum cylinder, instrumented with these sensors that could measure the vibrations of this bar as a gravitational wave passes by. That set the science world on fire. a number of people tried to replicate Weber's experiments and were unable to, and eventually they were found to be erroneous. But it set a whole field in motion of the interest in detecting gravitational waves. And then the final sort of end to all the discussion came from the discovery of I should say the first black holes were discovered in 1971. And I should say this was not, I shouldn't have said discovered, because this was actually quite controversial at the time. It was called the maybe black hole, the putative black hole. And it took 20 years for people to really sort of agree that it was a black hole. But the final sort of question in gravitational waves from neutron stars and black holes came from the discovery of Hulse and Taylor in 1974. And I'll tell you what it is, but I just want to mention that the discoverer, Joe Taylor, is in the room. I never tire of being proud of that, Joe. So what did they discover? They discovered one of these neutron stars that acts as a lighthouse, so a pulsar, but it was in a binary. It was in orbit with another neutron star. And so this now was two pairs of neutron stars that were orbiting each other. Now, ordinarily, when our Earth orbits the sun, it's going to, once per year, it comes back to where it was. And the next year, it does the same thing. And the next year, it does the same thing. And it closes its orbit and just comes back to where it was. With these objects, neutron stars in orbit around each other, they don't do that. In fact, as they orbit each other, they get faster and faster, and eventually their orbits get smaller and smaller, and they'll collide. Now, why do they do that? They do that because they are, as Einstein told us, they are radiating gravitational waves. And those gravitational waves, like any other wave, carry away energy. And that energy comes out of the orbit. So as the wave carries away energy, the orbits are shrinking. And that is indeed what Hulse and Taylor showed with this binary neutron star system that they saw. So here is their data. And I never noticed that this corner is getting cut off, but that's okay, we'll fix it. Never mind, I'll tell you that data goes to 2005. Okay, so, what's shown here basically is the year since the discovery of the object, PSR 1913-16, and on the vertical axis is a measure of the size of the orbit. And what you can see is that as a function of time, as time goes by, the orbit is shrinking. And these were the data points of their measurement, and then the solid line, it's not a fit to their data, it is the exact prediction that Einstein's equations would make for those pair of neutron stars losing their orbit shrinking because they're losing energy to gravitational waves. So this was seen as the sort of the definitive and final answer that gravitational waves exist, and in fact these binary neutron star systems radiate them, and Hulse and Taylor won the Nobel Prize in 1993 for this discovery. Now, why was Einstein so ambivalent, and was it justified? So I put up very few equations in a talk like this, but I put this one up because people who like equations will feel it. Okay, now what will you feel? So L is the luminosity in gravitational waves. It's the actual power being radiated in gravitational waves. C is the speed of light, and G is the gravitational constant. Those are constant. But now comes the interesting scaling. R is the size of the object, and R sub SH, SCH stands for the Schwarzschild radius. The Schwarzschild radius of an object is basically the radius it would have if an object of mass m were to be a black hole. So what's the radius it needs where light can no longer escape? And so what you see is that if an object has its size is comparable to the size of a black hole of the same mass, then you would get a large luminosity, so lots of radiation of gravitational waves. And then V is the velocity of motion of material in the object, and C is the speed of light. So when the object is moving close to the speed of light, then you also get a large luminosity. So the two ingredients you need from sources is they need to be compact. Their radius should be comparable to that of a black hole of the same mass, and they should be relativistic. Now, sources in the sky, sources like this, to make them in a laboratory is truly impossible to have any reasonable size of amplitude of radiation. But sources that satisfied these conditions were not known in Einstein's time. Einstein died in 1955, and remember, the first neutron stars and black holes were not discovered till the late 1960s. So his ambivalence was justified, and one of the things that really stuns me every time I think about it is that even though he was unsure about these things, he wrote down a theory that made very firm predictions about gravity, about space-time, and about black holes. And he did that without knowing that these objects could exist in nature. So here now, where we fast forward to some major breakthroughs in numerical, so computer-assisted solutions of those beastly equations of Einstein's. So this now is a movie that shows what space-time would look like for a pair of black holes orbiting each other. And what you're going to see in this movie is on the bottom here, you'll see how the ripples, the waves change with time, so their frequency and their amplitude will grow. And on the movie part over here, what you're going to see are the two black holes. The surface of this screen depicts space, and the color coding depicts time. And so what you see is when the two black holes are far from each other, you can see they each form their own little funnel of space-time. These are the famous funnels of space-time curvature in the vicinity of a black hole. But then as they radiate gravitational waves, their orbits get closer and closer to each other, and the space-time start to interact with each other. And you can see that it also starts to distort. And then eventually, as the black holes' horizons touch each other, you'll see the largest amplitude of distortion of the space-time solve. You can see big mountains and valleys. The movie slows down. And then at the moment that their horizons touch, you get the maximum amplitude of the signal. You can see very, very distorted space-time. And then they merge into a single black hole that wobbles for a bit, and then it just sort of sits in empty space quietly, never to be detected again. Okay? And then these gravitational waves spread out into the universe. Now, this is actually the work of a large collaboration of scientists who have been working for literally a couple of decades to solve this problem of orbiting black holes using the exact solutions to the Einstein equations. Now, life wasn't always this good. If we go back to the late 1960s, when neutron stars were first discovered, this man, Kip Thorne of Caltech, but who was here actually at the time at Princeton, he was among the early pioneers to think about what would a gravitational wave from neutron stars look like. And he did not have the luxury of exact solutions to the Einstein equations. He had to do approximation methods to do that. And he showed that, in fact, the amplitude of the wave, which we call a strain h, would evolve in this way. Its frequency and amplitude would increase with time as the two neutron stars or black holes grew closer and closer to each other. And he also put a scale on this. He's told us that if we put this pair of neutron stars, orbiting neutron stars, in a galaxy not too far from our own, we would expect the amplitude of the wave to be 10 to the minus 21. So I'll just make a pause here. This is a really, really tiny number. If you do not like to think about numbers in units of 10 to the minus 21, you can write it out for yourself. You would put a decimal point, you would write 20 zeros, and then you write a 1. Okay? And that would be the number. So it's a horrifically small number. I haven't put any dimensions on it, so at the moment you won't be too alarmed, but you can see that already for neutron stars, this is a small number, so the numbers Einstein might have calculated for ordinary stars would be many, many factors of millions smaller than that even. Okay? So then at the same time came the question, so this was the state of the art at the time in the late 60s of Thorne and others telling us what the signals from colliding neutron stars might look like. And in the meantime, there was also the question being asked of how one might detect gravitational waves. And to answer that question, we need to know first, what do gravitational waves do? And so the question there is, so we know from Einstein that there are these ripples of space-time and they travel at the speed of light. Now, a very important property for us here on the Earth, if we want to measure them, is that as they pass through us, through the Earth, through space-time objects, they stretch and compress the space-time itself. And what that really means is that as a gravitational wave goes through a space-time object, let's take me, I'm a space-time object, we all are. As it passes through me, in each half cycle of the wave, it stretches and shrinks me. So if a gravitational wave were passing through me with a period of 1 second, once per second I would shrink and stretch. You know, I would twice per second I would grow fat and squat or thin and long. Okay, that's the way to think about it. That's the effect. And as soon as you know that that's what it does, then you can think about how one might measure that, because we know how to measure space-time distances, right? So the change in distance between massive objects is change. Okay, so if you take some space-time distance L, and in that and pass through it a gravitational wave of amplitude h, that distance will change by an amount delta L. So that's part of why it's called a strain, because the amplitude is equal to a change in length per length. Now comes the rub. Thorne had already told us that we expect this amplitude to be about 10 to the minus 21 for these neutron stars in a galaxy not too far from our own. So now let's do the experiment. Imagine I am a space-time object. I'm an object of 1.6 meters in length. And as this gravitational wave passes through me with an amplitude of 10 to the minus 21, my height will change by 10 to the minus 21 meters. And now you should really be alarmed, because now I put a real dimension on this. I'm telling you that my height will change by 1/1,000,000th the size of a single proton as this gravitational wave goes through me. So how could we measure that? And that comes to our next hero of the story, which is Ray Weiss. Now, Ray Weiss in the late 1960s was at MIT, and he actually was working with lasers. And the other historical moment is that in 1960, the laser was invented. And he was among the first to understand that one could use a laser instrument called an interferometer to measure this shrinking and stretching of space-time distances. So the instrument is shown in this little simulation here. You start with a laser beam. You split that laser light so that half of it goes up to this mirror up here, and the other half goes to this mirror on the right. These mirrors reflect the light back. And then depending on the path length that each of these beams of light takes, either the waves will add up and you'll get all of the light out at the output, or they'll cancel and you'll get no light, and you can do everything in between. So the measurement in the end is you basically are measuring how much light comes out at the output of this instrument over here. Now, this idea was not uniquely proposed by Weiss, although he was among the early proponents. But what Weiss understood very early on was that you could not make this measurement if these instruments were laboratory scales, if they were just about a meter, if they were about our height. That would not be possible. He knew that you could not make measurements at this output of changes in distance of 10 to the minus 21 meters. So Weiss proposed that you should actually make this very long, make the space-time distance long. And if you did that, then if you made L a few thousand meters, or 4 kilometers in this case long, and then that same gravitational wave of amplitude 10 to the minus 21 would give you changes in path length of 10 to the minus 18 meters. And that, he told us, was easy to do. Yeah. He didn't say it was easy to do. This is another tour de force of the immense intellectual horsepower that went into these early ideas. In 1972, he laid out a very complete roadmap of what kind of instrument you'd have to build and what were the things you'd have to worry about in terms of noise sources to make this experiment work. Now, in 1975, Thorne and Weiss met quite by accident, and hashed up the idea that we should actually build these kilometer-long L-shaped interferometers. Here's the cartoon I showed. Here's the reality of the two instruments of LIGO, which is the Laser Interferometer Gravitational-wave Observatory. And to make this measurement work, you need to do two things. So really for the people who like to do experiments, this is the moment to sit up, because I'm going to tell you how the experiment is done. Okay? You need two things. So what is the measurement? The measurement we are making is we're measuring the motion of this mirror relative to the center here and this mirror relative to the center here. And we want those mirrors to move only because of the passing gravitational wave. And when the gravitational wave passes through, their relative motion will be that 10 to the minus 18 meters. So now my first question is, if I just put a mirror down in a lab over here, how much would it move by if I did nothing else? Does anybody want to guess? People who work in labs are welcome to answer. So it's typically a fraction of a micron. So let's say it's 10 to the minus 6 meters. So the mirror naturally moves by 10 to the minus 6 meters. The gravitational wave will move it by 10 to the minus 18. So that's your first factor of a trillion. Its natural motion is 1 trillion times bigger than the motion you want to measure. So you have to do some very fancy vibration isolation using systems like these, which actually measure the vibrations of the ground and cancel them before they reach the mirror. And then you can also hang the mirror from a pendulum, which is another way to filter vibrations. And if you do that, then you can get a mirror. If you do these tricks, you can get a mirror whose motion is 10 to the minus 18 meters at 100 hertz, which is the frequency at which we want to make this measurement. So that's the first thing. So you've succeeded in making the mirror very still. That would do you no good at all if you didn't also know how to measure this tiny motion. And clearly you can't use a ruler or ordinary length measuring techniques for distances that small. So in our case, we use the wavelength of the laser light. The laser light wavelength is the tick marks on our ruler, if you will. Now here comes our next factor of 1 trillion. The laser light that we use is near infrared, very close to visible, and its wavelength is also 1 micron. So that's 10 to the minus 6 meters. But we want to measure motions of 10 to the minus 18 meters. So really what we're doing, what I'm requiring is, I want to make a measurement that's 1 trillion times smaller than the tick marks on my measuring device, right? And the way we do that is by using an enormous amount of laser power so we can average over many photons. So we use high power lasers. In our case, we use 200 watts of laser power. And I'll just put that into perspective. I mean, this laser pointer that I'm shining up over here is about 5 milliwatts. So this is a very powerful laser. And then not only do we use this high power laser, but then we use a number of tricks in the interferometer that I won't explain that then boosts that power up to nearly 1 megawatt. So we have 1 megawatt of circulating power. And once you do that, then you actually can make this measurement. You make your mirrors very still. You average over the noise of your light beam, and then you've got yourself a measurement. And in fact, this was supported by the National Science Foundation since the early days, since the early 1970s, so well over 45 years from the time these ideas came about to the time the first discoveries were made. And then here comes the third hero of our story, and that's Barry Barish, whose role in this was to actually take these ideas of Weiss and Thorne and Drever and others and turn them from tabletop tinkering physics to national facilities. Okay? And now I want to pause here for a moment to also say, so this was supported by a federal funding agency for really 4 decades, and we've really thought hard about how could that happen, and what were the conditions that made that happen. And I would say there's a few things that are important. One was that Weiss and Thorne and others spent the better part of a decade on consensus building. First, to build consensus among scientists that this was A, doable, and B, worth doing, and then to build political will. And so this is the moment of time where I want to tell you that if anybody hasn't registered to vote, You have few more days, please do it. You know, where this is a moment in time when every vote counts, and I won't tell you which way to vote. Just register and fix this. Okay. And not just in the name of science. Okay. All right, so LIGO is one of a global network of detectors. So there's the 2 LIGO detectors in Washington and Louisiana in the United States. These are 4 kilometers long. The next operational instrument is the Virgo detector in Italy, which is a 3 kilometer long interferometer. There's a little 600-meter long interferometer that operates in Germany, but mostly in its present incarnation, it's too short to be competitive with these longer guys, so it's more of a test instrument. And then under construction is a 3 kilometer long detector in Japan called Kagra, which is located in the Kamioka mine. And then a planned observatory in India, and a planned space detector called LISA. Okay, so that's sort of the global network. Now, we fast forward from those early days of Weiss and Thorne in the 60s and 70s to September 14, 2015, when LIGO detected its first astrophysical signal. And that was the collision of 2 black holes. And by the way, the naming scheme you'll see from here on is GW stands for gravitational wave. 15 is the year 2015, the 9th month, the 14th day. So you can see how these objects, you know, when they were recorded in our instruments. So here is what happened. In a galaxy far, far away, 2 black holes collided. And then these gravitational waves traveled a long distance through the universe. This is a nice little movie because it shows how the gravitational wave distorts starlight as it passes through. But it also is a good reminder that gravitational waves pass through most everything unchanged. They found our beautiful Earth. They arrived at first in our Louisiana observatory and then 7 milliseconds later in the Washington observatory. And here is the discovery that shook the world. Okay? It didn't shake it quite literally this much, but it did. And that was registered by LIGO, by the 2 LIGO instruments as these data. And this is now a somewhat iconic plot. I want to point a few things out to you that I think are just incredible. So the first thing to notice is that on the horizontal axis is time. So this binary black hole system lived for of order billion years. And we measured the last few hundred milliseconds before the 2 black holes collided. Okay, so that's the first time. This is the scale of the measurement. And we didn't measure earlier times because at that moment they were orbiting each other too slowly to be in our measurement band. Okay, so they've been orbiting each other for those billion years, but we aren't able to detect those frequencies. Vertical scale, there's the amplitude of the gravitational wave in units of 10 to the minus 21. When those 2 black holes horizons touch, which is the maximum of the amplitude, the strain was 10 to the minus 21. So there's a big check mark for Kip Thorne. He told us this in 1967, 68, right? When those gravitational waves passed through our detector, the motion of the mirrors was a few times 10 to the minus 18 meters. So big check mark for Ray Weiss. He told us how to do that in 1972. Okay? So really just incredible. Now, if you could encode that signal onto a loudspeaker? So you've heard, and certainly the title of my talk even said you can listen to black holes. And here I want to be very clear. What's going on is it's not that black holes make sound waves that travel through a vacuum and reach us. They don't, because sound waves don't travel in a vacuum. What it is it's a metaphor for the fact that these black holes are radiating gravitational waves at a frequency that happens to be in our human audio band. So if you encode it into sound, you could hear it. And if you did that, then here's what you would hear. It's called a chirp because it sounds like a bird chirp. You've seen the waveform already. Oh, I have to turn this on from here. What it is it's basically a low frequency to high frequency, low amplitude to high amplitude. So if I were to simulate the sound, it would be like whoop, And this is the actual sound that that was encoded in that data. Let me see if I can get this to, I lost my cursor. Here we go. You can hear that's the thump. And now this has been sped up by a factor of 2. It's like color coding the sound, but it's coding it for our ears to hear better. And so I was especially happy to put this in here because, I'm being hosted by the Council on Science and Technology, and here is a case where art and science mix. This is our perception of hearing, and really what it is the ripples of space-time. We can hear these by encoding them onto a loudspeaker. Now, how cool is that, right? Okay. Now, what can we learn from those signals? So that's a fun thing to see. So this is now that same signal that I showed you that was measured, but this is the best fit model to it. And I put this up here because you can think of this process in sort of 3 phases. There's a phase where the 2 black holes are just sort of orbiting each other and getting closer and closer. That's called the in-spiral. And then eventually they collide with each other, which is the merger. And finally, there's this phase called the ring down, which is simply the black hole, the newly formed black hole wobbles, and then the emission shuts off. So from the way that the frequency evolves, from the fact that the frequency is changing with time, it's getting faster, you can determine the mass of the black holes. Once you know the masses of the black holes, from the amplitude, you can determine how far they are from us. And then finally, by looking at this last part of the signal where it's decaying, you can tell what the mass and spin of the newly formed black hole was. And from those things, you can construct what happened. So I will tell you now the story of the 2 black holes. So once upon a time, 1.3 billion years ago, there were 2 black holes. And they orbited each other and radiated gravitational waves. Now, I actually like this simulation in particular because it uses the same tools that was developed by Kip Thorne's group for the movie Interstellar. If you haven't heard of Kip Thorne for the Nobel Prize, you might have heard of him for Interstellar or vice versa. He was the sort of the scientific brains behind the movie Interstellar. And you can see how these black holes distort the starlight. They collided, and they formed there's this newly formed black hole. And from that process, we could tell the following. We could tell that the parent black holes were about 30 times the mass of our sun. At the moment that they collided, they were moving at about half the speed of light. So you really have to pause here for a moment. Think about this object, 30 times the mass of our sun, 250 kilometers in size, and it's moving at half the speed of light. This is the most extreme things that nature can do. We know they were 1.3 light years away, and remarkably, we know then that the newly formed black hole was 3 times the mass of our sun lighter than the 2 parents. So 3 times the mass of our sun was radiated away in those 200 milliseconds in gravitational waves. And that is an extreme amount of power. The amount of energy per time that was radiated was more powerful than any explosion we've seen since the Big Bang. Okay? So it's a very, very extreme system. Now, we also know that they did not live happily ever after. And I'll just say, this is very much like us human parents. We sacrifice ourselves for our children. So a new black hole was born in the destruction of the 2 parents. Okay? Now, there have been more collisions of black holes since that first one, and here's a sort of list of them that kind of tells you the dates. There were 2 more in 2015, then LIGO shut down for a year to make improvements. When it came back for observing run 2, there were 3 more seen in that second observing run. And what's really important, I'm going to fast forward to this object here. So this is on August 14, 2017, and that was actually another watershed event because for the first time our partner observatory in Europe, the Virgo detector, was also observing. So now 3 detectors were observing together, the 2 LIGO and the 1 Virgo, and they all 3 saw this object. So this basically is a plot on the left, simply shows that the purple curve is Virgo, and it's not as sensitive as the 2 LIGO instruments were. The lower these curves go on the scale, the more sensitive they are, and you can see that. So the most sensitive was the LIGO Louisiana detector, saw the signal the strongest. The Washington detector saw it a little bit weaker, and then the Virgo detector saw it somewhat. but between each of them saw it strongly enough that you could reconstruct what they each saw. And then came sort of the real beauty of having had this 3 detectors going at the same time, which is that the analogy to listening extends a little bit further. So gravitational wave detectors are like our ears in another way, which is that they don't have very good directional sensitivity. The way that we hear is we reconstruct the direction from which a sound came by triangulation with our 2 ears. And the same thing is true for gravitational wave detectors. So the more of them you have and the larger the separation between them, the better they can tell where the source came from. And that was the beauty of having Virgo. So before Virgo was on, LIGO's detections were, all we could say is, well, this black hole collision happened in this big patch of sky, this 1,000 square degree patch of sky. We don't know exactly where in that patch it was. Now, if you tell your astronomer friends to go point their telescopes to see if they see something with light, and you tell them, well, it's somewhere in this 1,000 square degree patch of sky, they laugh at you because telescopes have this tiny, tiny fraction of a degree field of view. It would take them many, many nights to tile over such a big region. But as soon as we added Virgo, we have a 3rd ear, and our localization becomes much better. See the little patch over there? In fact, you can see exactly what it was. With the 2 LIGO detectors alone, all you could see was that you could limit it to this 1,200 square degree patch of sky, but as soon as you added Virgo, you could then limit it to a 60 square degree patch of sky. And that was very important for localizing, to say where in the sky did this happen. And that story will continue in a couple of minutes with something that happened 3 days after this one, but let me just close up the idea of what we've learned from black holes. What we've seen is that we see black holes with all these different morphologies. You can see signals that last a long time, signals that lasted very short, and all of these different shapes tell us about the masses and the distances of the black holes. And from that, we have started to construct a picture of black holes that we haven't known before. Before these discoveries with LIGO and Virgo, we thought this category of black holes called stellar mass black holes, based on those X-ray emissions I showed you at the very beginning, were about, those heaviest ones were in the range of 10 times the mass of our sun. And the LIGO-Virgo detections show that these black holes are actually quite a bit heavier. And that has left us with an interesting conundrum. We actually don't know how nature makes these heavier black holes, which is another beauty of discovery, which is that as soon as you make a discovery, all you've done is ask a new question, right? So here are some things we know and some things we don't. So we know from these first detections that Einstein's general theory of relativity seems to be correct. We can measure that the gravitational waves travel at the speed of light, and they seem to have the geometry that we would have expected. We also know now definitively that these black holes exist and they even form pairs. We hadn't known that with certainty before these first detections, certainly that they could form pairs. Now, what do we not know? Well, how does nature make such heavy black holes? We don't know for sure. How do they form pairs? We don't know for sure. We have some ways of finding out. I'll give you an interesting story. We know that black holes can spin about their own axes as they're orbiting each other. And so you can imagine that by measuring these spins, if these black holes form pairs because they're born as twins from a pair of stars, then their spins should be aligned, because as they orbit each other, the angular momentum requires the spins to align with each other. On the other hand, if they're sort of drifting alone black holes in space, and they just happen to meet each other and dynamically capture, then their spins should be randomly oriented relative to each other. There's no reason for their spins to be aligned. And those are the kinds of questions we could start to ask, but our data set is too small and not yet accurate enough to really make any definitive answers for that. But that's the black hole science we've done so far. Then we fast forward to 3 days after the triple detection with Virgo, and we see another spectacular event, which is the first binary neutron star collision. Now, neutron stars are actually important and different than black holes in that neutron stars are not black. They're made of neutrons, and when they collide, they should give off spectacular light show. So, and that is indeed what happened. LIGO and Virgo detected the pair of neutron stars colliding, and that was followed by a spectacular light show that was actually observed by over 70 telescopes worldwide. So let me tell you that story. It's fun. So on August 17, 2017, LIGO detected this signal here. This is LIGO, one of the waveforms from LIGO. And the very first thing you notice in this particular way that I've shown the signal is that it lasted over a minute. And that immediately told us that it was a light object and therefore likely to be neutron stars, not these heavy 30 solar mass black holes, but in fact 1 solar mass neutron stars. 1.7 seconds after LIGO and Virgo detected the neutron star collision, a very bright signal was detected in gamma rays. Okay, this is the first time that one could see something that was seen in gravitational waves, and a short bit later that an object lit up in gamma rays. LIGO and Virgo together could localize this source to this 30 square degree patch of sky that happens to be in the southern hemisphere. When we detected this signal, it was daytime in the southern hemisphere. So astronomers, we alerted the astronomy community, and astronomers had something like 12 hours to prepare their telescopes to go look in this patch of sky. And then what followed was something that, you know, I would call sort of a physicist and astronomer's night to remember. Okay? And so this is a very busy plot, but I want you to take away only this idea. No matter what color of light or gravitational waves you looked in, something was seen. Gravitational waves first, then the gamma rays, X-rays, ultraviolet, optical, infrared, radio. And each of these colors and on this timeline tells you when a certain color of light was seen. And so in every color of light that we've looked, we see an object. Now, what did we see? So here's a whole panel of telescopes pointing at a particular galaxy. This happens to be galaxy 4993. And you see these crosshairs are all lined up against this little dot over here, right? Every one of these telescopes saw something in that crosshair. Now, why is that so interesting? And the time here was 10 hours, 11 hours, etc., 9 days after the gravitational wave trigger. Now, why that's so interesting is if you take just this panel here, this is the telescope DLT-40, and if you looked at the same galaxy 20 days earlier and look at the crosshair, there's nothing there. This object lit up in the sky that night. Okay? And that's what we expect. So now here is a movie of what really might have happened, which is that you had these pair of neutron stars orbiting each other and giving off gravitational waves. They get closer and closer, and then as they collide, these neutrons are in a very energetic collision. Those beams are the beams of gamma rays, and then this is the isotropic radiation in other wavelengths that came. I'll play it again so you can see what happened. The music is very dramatic, and that is thanks to NASA. This is a movie made by NASA. So I'll show it to you one more time so you can really see what was going on. What you should see is initially only gravitational waves. Then the first thing that comes out are the gamma rays, which are very beamed. It's those jets that come out. And then as these neutrons collide at very high velocities, what they're doing is, remember, atomic nuclei are made of neutrons. So what they're really doing is in real time, they're fusing elements of the periodic table. Okay, as these neutrons come together. And that's where all the light is being given off from. That's the energy being released. So let me see if I can do that again. All right, so gravitational waves initially, and then look out for the jets. That's the gammas that come out first. That was seen 1.7 seconds later, and then all the other colors of light come out of that cloud in the middle. There's the gammas, and then right here, that's all the other radiation, and there's where all the elements are being fused. Okay. All right, now this is a movie of a spectrum. These are different colors of light, and as you see, as days go by and the telescopes are observing, these different peaks that you see that show up, some disappear, others show up, is a direct measure of elements of the periodic table being fused in that neutron star collision. Okay, so we are actually seeing in real time nature making, in this particular case, heavier elements like gold and platinum. Okay? And therefore, this neutron star collision has also been dubbed nature's gold mine. Okay? Now, I'll finish my story by telling you that this one observation of a neutron star collision in gravitational waves and with all these telescopes has really helped us solve some decades-long mystery with a single observation. So the first decades-long mystery was, for a long time, astronomers have speculated but haven't known for sure what causes this particular class of gamma ray bursts. So we see these gamma ray bursts. Certain gamma ray bursts we know are associated with supernovae, which are those exploding stars. But we haven't known how to explain this particular short, very energetic bursts. And now we see for the first time that neutron star mergers are indeed the cause of these short duration gamma ray bursts. The fact that gravitational waves saw the neutron star collision and then shortly afterwards the gamma ray burst was detected for the same object tells us that it confirms this speculation that's been around for decades. Another mystery that has long existed here on the Earth is, believe it or not, we have too much gold. And what that really means is we don't know where all the gold we see here in the Earth comes from. We believe that these elements are fused in the nuclear reactions of stars, like our own sun. But stars can't fuse very much of the heavy elements because they don't have enough neutrons to do that. Remember, heavy elements have many neutrons in their nuclei. And so the alternative was that some of these heavy elements like gold and platinum get made in supernovae. It turns out that doesn't explain the abundance we see here either. Even supernovae don't have enough neutron-rich material. So it has been thought that perhaps these neutron star collisions should be the place where gold and platinum get fused in nature. And indeed, that's what we saw with that spectrum I showed you. And in fact, you can now populate this part of the periodic table where the yellows show you what fraction of those elements were actually formed in the neutron star collision. And that starts to explain the abundances of the gold and platinum and the heavier things like lanthanide series we see here on the Earth. And then finally, a last thing that you could do with this one observation is by being able to see the gravitational waves coming from this neutron star object and measuring their speed, you could actually say something about the Hubble constant. Now, many people glaze over when you say the word Hubble constant because it's an obscure cosmological measure. Now, I'll tell you why you shouldn't glaze over. The Hubble constant controls the history and the future of the universe. So you should care. And what you can see from this first measurement with gravitational waves is that with other methods using the propagation of light in the universe, there has been a discrepancy between what exactly the Hubble constant is, and the gravitational wave measurement turns out to be not as accurate as those other two measurements, but in the same ballpark. So gravitational wave observations confirm that the history and future of the universe is sort of like we think it's going to be. Okay? All right. Now, I'm going to finish up by just telling you, so my claim is that we're launching a new era of gravitational wave astrophysics. So let me just finish up by telling you why I think you're witnessing an important moment in scientific history. So these first detections of gravitational waves are the first confirmation that's a direct measure of space-time wiggles, right, ripples. Really, these peaks and troughs you see are really the ripples of that space-time itself. We see early confirmation of this piece of Einstein's theory of general relativity, which is the wavy part that hadn't been tested with observations before. We see that black holes and neutron stars can form in binaries, and those collisions have been observed in real time. And as someone who spent 27 years of my career on building the instruments, it's also really nice that the damn instrument works and with the precision that it needed, right? So that's a nice thing. But I'll tell you, these are the things we celebrate today. This is not what will live on. what we've really done, and which is the game changer, is that we've really turned on a new way of looking at the universe. We no longer need to rely only on light. We can use gravity to look at things that don't emit light. And black holes is one example. We don't know what else could be out there. I think many of us expect there will be those discoveries. So the way to think about this is to look back at what Galileo did with telescopes. So we believe Galileo in 1609 was the first person to point a telescope at the sky. And nobody remembers or particularly celebrates what he saw. He saw that the planet Venus has phases. He saw craters on the moon. And we don't remember or celebrate that because we can see those things much, much better now. Because a toy store telescope is more powerful than the one that Galileo had, right? What Galileo did, though, was extremely important. He made a paradigm shift. He said to us, for the first time, we humans don't have to rely just on our naked eye to look out at the sky, that we can use instrumentation. And from that paradigm shift, we've made amazing instrumentation. We've put 100-inch telescopes up. We've put 100-inch telescopes in space. We're now building 25 and 30-meter class telescopes. In the meantime, we've also turned on different telescopes with different colors of light that our eyes couldn't see. And from that, we have constructed a view of the universe that Galileo could never have predicted. And that's where we are. Gravitational waves are no different. They also span 20 orders of magnitude and wavelength, just like light. And all we've done is look at these, with these terrestrial interferometers like LIGO and Virgo, we have looked at just the first little piece of the gravitational wave spectrum, and there's lots more to see with different instruments and different techniques to map out the gravitational wave sky. So that's the real revolution you're witnessing. Thank you.
So thank you very much for that beautifully clear talk and the beautiful results. I think we have time for a few questions.
Sure.
How large, it's two questions actually, how large is the catalog of simulations in the simulating extreme spacetimes, simulations, whatever. And the, I think you know what I'm trying to say. And the second question is, it's not always 3 solar masses of gravitational energy being carried away. So what is the correlation between the difference in masses, or between the objects that are colliding, specifically for black holes and specifically for neutron stars?
Okay, so 2 questions were asked. One was, how large is the catalog of black holes that have been simulated by these by the simulations, like the extreme space-time simulations? So literally thousands of objects. The way this is done is you make yourself a grid of all possible mass combinations, and from those mass combinations you then calculate what the waveform would look like. And so each combination of masses, you can have 1 solar mass, 3, 2, 4, etc. And then you take the data and you take each of those waveforms and you ask which one fits it the best. And then you do a refinement. Once you find one that fits better, then you can refine and fill in the mass differences between those and do a refinement. So literally thousands, 200,000 or more can be used at any given time. So that's the first question. And then the second question was that in that first black hole collision that I showed, 3 times the mass of our sun was carried away. But it's not always 3 times the mass of our sun. Could it be something else? And the answer is yes. It depends on what the parent masses were. So it depends on the component masses. So yes, that's actually given by general relativity. So yeah, I'll come.
Okay, non-science. But ever since I started following the gravity, the LIGO and all the rest of it, my question has always been, you found the waves, but in my rather prosaic, I'm thinking, can you do a double slit experiment with a gravitational wave?
Yeah, so your question is, could you somehow cause gravitational waves to interfere? Yeah. So the answer is in principle yes, but these are too incoherent. They're basically their phases are too random relative to each other for interference to be observable.
Okay, so you couldn't actually use that kind of experiment to determine whether or not they were actually particles and waves at the same time?
Oh, now you're going into the quantization. Now that's a really unknown territory. But the truth is, we have everything I've shown you is purely classical gravity, because we have very little handle with these instruments certainly to do anything in the realm of quantum gravity, with one exception, which is you can say, let's pretend that we don't know how to quantize gravity, which is true, we don't. But that we could, all right, so theorists are objecting to such a strong statement. So let's say, I'm an experiment, let's say I don't know how to quantize gravity. But what I can do is I can measure the dispersion of the waves that I measure, and from that I can put a limit on, from the dispersion I can put a limit on what the mass of a graviton could be in this theory. And we've done that. We can do that with our data, but it's a bound on a mass for a particle that in the theory should be massless, and it's a small number. So it's not like we found a heavy graviton. We found a very light. We've bound it to be very light. So. Paul.
So when black holes collide, you get a bigger black hole.
Yes.
And so my question, I guess, then is what happens when the pulsars or the neutron stars collide?
So that's a very good question. So when a black hole collides, you must make a bigger, heavier black hole. When neutron stars collide, there's a couple of possibilities. If the two parent neutron stars were light enough, they may just form a heavier neutron star. But more likely what will happen is that when the masses of the two neutron stars combine, it's heavy enough that it will just collapse into a black hole. And so that that would be, that's a process that we would love to be able to see, and eventually we should be able to, but that process happens at a frequency of close to a kilohertz, which is where our detector sensitivity is starting to not be good enough. So we'd either need a neutron star collision that's close enough in that the signal is strong enough that we can see, or we need to make improvements to the detectors, which we're working on. So, yeah.
Presumably there's a lot of these ripples going through the universe, and I would imagine that they kind of can interfere with each other or run into each other. So do you expect that there would be kind of interference so that they would combine together?
You mean the black holes themselves?
Or that the gravitational waves?
Yeah. So the waves can intersect, and again they're incoherent with each other. They have random phase relative to each other, so they wouldn't form a recognizable or measurable interference pattern. For the same reason that if I took two laser pointers and I just shown them through the same region of space, they wouldn't see an interference pattern unless you arrange their phases to be in lockstep with each other. So yeah, that's the same idea. So you wouldn't see interference. Catherine?
So you guys have measured a handful of events, which must tell you something about how many black holes there are in the universe. And are there more than you thought, or are there about the right number, or fewer? I mean, it seems like they're all...
Yes, and yes. Okay, so what did we know about the number of these binary black holes before we made these detections? We knew we had a range, and it was actually a really big range. There's famously a joke that in astronomy the uncertainty is in the exponent. And in this particular case, it turns out to be true. There was a sort of over a factor of 100 in the rate at which you would expect these binary black holes to be merging. Okay? And so what we have found is comfortably in sort of the center of that range. And there was a great deal of uncertainty because there were and still are so many unknowns. So how do these black holes form? We think they form from binary stars. So we know how many, in a given galaxy, how many stars are in binaries. But what we don't know then is how many of them will collapse and not break apart the binary as they collapse and go supernova, etc. So there's many uncertainties. So the people reconstructed these in statistical ways, the rates, and it's in the middle of the range. So.
If I could ask
Yes,
a
sure,
follow-up
Dan.
on that. What I understood you to say is that there are more massive black holes, there are more massive black holes than you had expected. Does that mean there aren't as many of the light ones, or you just aren't sensitive to them?
Yeah, I think it's the latter. And as our instruments, as the low frequency sensitivity of our instruments improve, we should become more sensitive to the lighter ones. So, yeah, go ahead. Right, next down. Yeah, go ahead.
So obviously the universe is expanding. Hubble said that. So are you worried about /2 Doppler shifts affect your data at all?
Yeah, so yeah, definitely, these waves will be redshifted like any other wave, and we account for that in the analysis. So you do the analyses in our observer frame or in the source frame, and that accounts for the redshift of the waves.
You said something that just begs me to ask the question. What does the Hubble constant say is the future of the universe?
Nominally, the universe is expanding, and that acceleration is slowing down. Maybe I'll ask the cosmologists to answer that. Herman, you wanted to say?
It keeps expanding.
Right.
Given that there's dark energy,
that's
the universe
slowing
keep,
down.
But it will keep expanding.
Yeah. Which of course then should beg the next question. That means everything is just going to keep moving farther and farther apart, and eventually everything will be so far from everything else that it should just turn dark and gloomy, right? So,
Maybe one last question.
How does the gravitational wave power change from the direction in the plane of the orbit to perpendicular to that? So, in other words, if the gravitational waves radiated perpendicular to the plane of the orbit, it was zero, then LIGO wouldn't be able to see mergers that were oriented in a certain direction.
yeah, and that's right. So there are orientations that we would that are optimal, and orientations we would be absolutely insensitive to, and so that's exactly right. And so we're most sensitive to the when we're face on to the orbit.
Okay, so thank you very much once again.